Hello and welcome to lesson 12 on differentiability. So, differentiability we already saw in lesson 10 a little bit, but today we're going to be making connections to algebra with differentiability as well as the graphs. And your learning goal today is to determine whether a function is differentiable by analyzing continuity and identifying points of non-differentiability. So, today's lesson will be a little bit shorter, but I have additional work posted for you on Google Classroom, as well as some additional videos to go over the concept of differentiability to make sure you're fully understanding it. But let's get started with our lesson. So, just a reminder of the definition of differentiable. A function f is differentiable at x is equal to a if f prime of a exists. So if the derivative at the point x is equal to a exists. And when that point does not exist, so whether that's the limit or just it's, yeah, the limit is not does not exist at that point, we say f is not differentiable and the derivative does not exist. And don't forget our notation, d and e does not exist. So first for the function f of x is square root of x, you're asked to find which point the function is not differentiable for. So first we have to consider the domain of the function itself, right? So again, this function kind of looks like this. And so the domain of the function itself is x greater than or equal to 0. So when you're thinking about differentiability, we have to consider the values for which the function actually exists to begin with. Now, for these values, consider that at x is equal to 0. We do have that the limit of x approaching 0 from the right of square root of x is equal to 0. So pretty much if you start at any point, so I gave you the example of x is 1, and you start getting closer and closer to the point 0, 0 here. And you're pretty much decreasing the difference between your inputs such that we are trying to get that instantaneous rate of change at x is equal to 0. Then we can see that the limit as x approaches 0 from the right exists. We're just getting closer and closer to 0 from, if you look just even from the function itself. Now, if you try to find the limit of x approaching 0 from the left-hand side, you'll see that this limit does not exist. And the reason for it is if I want to pick any point here to start approaching, I have no point here to pick. The function isn't defined for values of x greater than, or sorry, x less than 0, so we can't approach x from the left-hand side. And for that reason, this limit does not exist. And if you remember from the definition of a limit existing, we need the right-hand side and the left-hand side both to exist and for them to be equal. But because in this case both of those limits do not exist, and that's not to say that both like we clearly saw one of them exist, but together we don't have two limits, and so they can't be equal to each other because one of them is undefined or a limit that does not exist. Then we say that the derivative of f of x at that point also does not exist because similarly, if you find using that derivative definition with the limits, you try to find that, you'll see that you have no point from the left-hand side to approach. And so then we would say the function is not differentiable at x is equal to 0. And one thing to know here is we do have the point f of 0 is equal to 0. So the function itself is defined at 0, x is 0, but if you try to find those limits, we see that the derivative would not be you would not be able to solve for the derivative, so the function would be undifferentiable or it's not differentiable at x is equal to 0. Now let's look at another example, which is our absolute value function. And here you're all just asked, why is this function not differentiable and x is equal to 0? And if you remember when we first saw differentiability with the graphs, this is a corner, similar to a cusp. At cusps and corners, we know that the function is not differentiable by the graph. But now let's see why algebraically it does not exist. The limit does not exist, or the derivative does not exist. So in this function, um, for any value of x less than 0, we know that the slope is -1. But for x greater than 0, the slope is 1, which results in that corner there to begin with. Now, f prime at 0, which is that x is 0 that we're trying to find, is given by this definition of the derivative, so f of 0 plus h minus f of 0. But this part is just f of h, and the 0 is just 0. So we're left with f of h over h. And f of h is the absolute value function, but this has two cases. So we have to consider both cases here. And if we try to look, and that's the two cases we have here, 1 and 2, and it actually coincides with our left-hand and right-hand side limit. So from the left-hand side, if we're approaching 0, we see that the absolute value function is -h because it has that negative slope. So now by substitution, these would just be cancel out to -1, and this is just -1. So the slope of the tangent at all of these values would be -1. However, from the right-hand side, we have the absolute value function is actually just h. And h over h is just 1, +1. So the slope here is 1. So the left-hand side and the right-hand side limit do exist, but they're not equal. And so we would also say that the limit of h approaching 0 of, and this is our definition of the derivative, this does not exist at and keep in mind this is at x is 0, right? And that's because of that 0 and 0 there. And so because this limit does not exist, then we also say the derivative does not exist, and so the function is not differentiable at x is 0. And same with above, keep in mind that the function is still continuous at x is 0 because we just go, we can draw our graph without lifting our pencil, but differentiability and continuity are not the same thing. So you can have a continuous function that's not differentiable at a specific point. Now, consider this graph here, and you're asked for what values of x in this graph is the function not differentiable. And lesson 10 would be really useful here to go back to it to look at. But first, we are considering the points where the function is not continuous. And clearly we can see that happens at x is -8, and at x is 3, and at this asymptote over here. So we would say, first start with your discontinuities. And we have a hole at x is 3, and we have a jump discontinuity at x is -8. And so in both of these cases, we also, not only do we not have continuity, we also don't have differentiability. Next is the vertical asymptote. And actually this one would be a discontinuity as well, but soon working with derivatives, asymptotes have their own important role, so I'm going to start distinguishing them. So it's going to be its own category here. And this happens at x is 0. And so here we can also see it's not differentiable. So there would be no tangent for us to draw here. And same with here, same with the other two discontinuities. You wouldn't be able to draw any tangents here in any way because it's not continuous, so we can't have that slope. And two other points here oh, would be our cusps and corners. And pretty much think of these as the function having a sharp corner. So um, the rate of change will be the instantaneous rate of change will be those vertical tangents, and this actually happens over here and over here. So x is -4 and at x is 2. So we can see that for 5 values of x, our function is not differentiable based on its graph. Oh, and one thing to point out as well, we can see that at the cusp and over here as well, we do have continuity, but again, we wouldn't say it's differentiable simply because of the behavior of the tangent or the instantaneous rate of change wouldn't just not exist here. Now, here you're given three graphs, and you're asked to state the domain on which each function is differentiable. So we want now in set notation to represent when the function is differentiable. So let's start with our first example here. We clearly have a vertical asymptote here at x is equal to 3. Or sorry, -3. So we can say the function does not exist at x is, oh, this should be -3. And so the derivative does not exist either. Because, again, remember, it has to be continuous to begin with, and then we can have differentiability. But if it's not continuous to begin with, then it's also not differentiable. And so the way we write the domain is as follows here. So we say the domain, and this is the domain of the derivative, okay? So x is in the set of real numbers, and also x is in this is domain of f of x, given that this is f of x here. And, oh, this also should be negative. And x is not -3. And that is already perhaps defined in the domain itself. We know that x cannot be -3, but just included it here as well. Now look at the second example over here. This one is a continuous function. I can draw it without lifting my pencil, but we can see over here at x is 4, the tangent would be a vertical tangent. Because of the movement of the graph, you can see we're having a turn there. So here the function is actually defined for all values of x, but we have a vertical tangent at x is equal to 4. And again, this is because of that turn in the function. So we say the derivative does not exist at that point because it's a vertical tangent. And the domain here, we write x is in the set of real numbers, always start with that. X is also in the domain of the function f of x, and again, keep in mind here, this is f of x. And here, x is not equal to 4. So the key difference here now is 4 is defined in the domain of the function itself, and that's why it's important to always just get in the habit of adding that, because you just want to acknowledge that you know that that is not differentiable at that point. So in the domain, we do have x is 4, but in the domain of the, so maybe I'll add this here. This is the domain of the derivatives. We don't have x is 4 anymore. Now, let's look at our last function. And again, this is f of x here. And this is similar to the square root of x function where we have a right-hand side limit, but we don't have any left-hand side limit at x is equal to -2. But again, x is -2 is defined for the function itself. We do have f of -2 is equal to 0, but we'll see that the derivative would not exist here, so it is not differentiable at x is equal to -2. And yeah, exactly like I said there. So here we have a restricted domain that x has to be greater than or equal to -2. And so we don't actually consider any of the other values that are not in the domain. So we only consider the values in the domain, but within those values, we have to have that x is not equal to -2 because we just saw that the limit would not exist there. So we don't have a tangent because I wouldn't be able to draw a tangent here. And so again, we write the domain of the derivative function is x in the set of real numbers, and x is in the domain of the main function, and x is not equal to -2 here. And same thing as above, x is equal to -2 does exist in the domain, so that's why you have to include that here to say that it's not in the derivative function, so it's not differentiable, and x is -2. And why is it important to include that x is in the domain of f of x? The reason for that is if you don't, then you would pretty much have to write here x is greater than -2. And you're doing an extra step where you have to consider, like you're making yourself consider all the points that are outside of the domain. And again, with derivatives, it has to be part of the function itself. So that's why it's always important to include that because you're acknowledging that you consider the domain of the main function, and now you're giving the restrictions based on that domain. And that was it for our lesson today. So again, a quick lesson, but on Google Classroom, there's two videos posted for you. One is a connection between continuity and differentiability, and another one is proof of differentiability. So they are a little bit extension pieces, but I highly recommend you watch them, especially if you're still struggling with the concept of differentiability. Hopefully, seeing other videos and perspectives will clear that up for you. There's also some practice questions here for you and an exit ticket to reflect on your learning so far. And as always, if you have any questions, please don't hesitate to reach out, and I'll see you all next class.